During the absorption lab, there were 4 main objectives that had to be met. The first objective was to characterize the dependence of NTUs and HTUs on gas and liquid flow rates. The second objective involved the characterization of the mass transfer coefficient through both experimental and literature data. For the third objective, the absorption unit was simulated using Aspen Plus software. Finally, for the fourth objective, the flooding condition of the column was characterized by measuring the pressure drop at different air and liquid flow rates.
This laboratory experiment will focus on gas absorption, which is a method used to separate gas mixtures that may consist of impurities or contaminants to recover and purify products. To quantify and analyze mass transfer, two-film theory is used to examine the gas-liquid interface where the absorption is occurring. The driving force in physical absorption is the concentration gradient that causes ions or other small particles to move from regions of high concentration to regions of low concentration. Here, the gas solute is being absorbed or transported into the liquid phase where phase equilibrium is assumed at the solid line separating the gas and liquid films. Henry's law can be used to describe that equilibrium where Y is the gas phase mole fraction of component I and Xi is the liquid phase mole fraction of I. Henry's constant Kh is dependent on composition, temperature, and pressure and can be derived from literature data. The rate of mass transfer for both the gas side and liquid side can be described using the vapor and liquid fluxes. Those are shown using a K value for vapor-liquid equilibrium. At steady state, the molar fluxes are assumed to be equal and that there is no accumulation in the film layers. The composition at the interface is very difficult to measure, so it is common to use the fictitious liquid and vapor mole fractions at equilibrium. X star is the fictitious liquid mole fraction. Similarly, Y star is the fictitious vapor mole fraction. Using the bulk liquid and gas composition expressions and equating the molar fluxes for the gas and liquid phases, the equation in red is used to describe the driving forces that exist at the gas-liquid interface. Uppercase Kx and Ky are the overall mass transfer coefficients, which should not be confused with the lowercase kx and ky, the local mass transfer coefficients. Another equation for ky, the overall mass transfer coefficient, based on the gas phase is also shown here. This equation will be discussed in further detail later, where it is used to calculate the overall mass transfer coefficient from the local liquid and gas mass transfer coefficients from literature correlations. Now, I bet you're curious about how mass transfer relates to the other transport courses. Here's Dr. Gerke and Caitlin to explain to us how heat, mass, and momentum transfer can be related.
I could talk about one of my favorite things, heat, mass, momentum analogies. This is the concept of the Chilton-Colburn J factors. Okay, the J factor for momentum transfer equals the J factor for heat transfer equals the J factor for mass transfer. And we just stick the D there because otherwise it would say the same thing as momentum. And so the J factor for momentum is the friction factor divided by 2. The J factor for heat transfer is the Nusselt number divided by the Reynolds number, the Prandtl number to the 1/3, and the Schmidt number. And the J factor for mass transfer is the Sherwood number divided by the Reynolds number and the Schmidt number. And now, to me at least, the idea that there's any connection between the friction factor and the heat transfer coefficient that's buried in the Nusselt number and the mass transfer coefficient that's buried in the Sherwood number doesn't seem to make any intuitive sense to me. So we just observed momentum transfer and the water was cold. Okay, so you saw the momentum transfer go from a finite value to 0, and now the warm board is heating up the cold paper towel, so I'm getting heat transfer at the same time. And when I pull this off, you can see some of the green dye that's transferred also from the wall on this. So we're seeing then that essentially the momentum transfer, right, is transferring heat at the same time, and it's transferring mass at the same time. So the number of times that the paper towel basically hits the wall, that's the momentum transfer, is going to determine how much heat gets removed. It's going to determine how much mass is removed. And so again, the Sherwood number for the gas absorption experiment that you need is the mass transfer coefficient times the characteristic length divided by the diffusivity. And so again, what this means is with the Chilton-Colburn J factors, the momentum heat mass transfer analogies, and says that you can use a pressure drop measurement to get friction factor, which will allow you to get a heat transfer coefficient buried in the Nusselt number, which will allow you to calculate a temperature difference, but you can also use this then to get the Sherwood number, which will allow you to calculate a concentration difference.
Cool, thanks Dr. Gerke. Now moving on to the theory section.
Here we examine a packed absorption column where counter-current vapor-liquid flow. The differential material balance expressed here, where A is the mass transfer area per unit volume of packed bed, and S is the cross-sectional area inside the tower. Rearranging this equation and taking the integral of this equation, we can obtain an expression for LT, the theoretical height of an absorption column. An analytical solution can be used to describe the term in the second bracket, and that full derivation can be found in many textbooks. But for time's sake, the final solution is presented here. This expression was used in experimental calculations. The right-hand side of the equation above can also be expressed as the product of two terms: the overall height of a gas transfer unit, HTU, and the overall number of gas transfer units, NTU. The height of a transfer unit, HTU, is a measure of the overall efficiency of the equipment, which is dependent on the mass transfer coefficient, KY, A, the surface area of the mass transfer per unit volume, or effective interfacial area, which is determined by the packing. The number of gas transfer units, NTU, is the measure of how difficult it is to perform the separation, and larger values simply imply that the design of the column is ineffective. This expression is shown in red. From this experiment, we can solve for NTU. Using that value and the theoretical height, we can also solve for HTU. By rearranging the expression for HTU, we can solve for KY, the mass transfer coefficient, with respect to the gas phase. This expression was used to solve for the experimental mass transfer coefficient. Knowing that the units of an HTU is a unit of length, meters, we can determine the units for the overall mass transfer coefficient KY. Here, V is the overall gas flow rate with units of moles per second. A is the interfacial area per volume and has units of meters squared per meters cubed, and S, the cross-sectional area, has units of meters squared. Performing a dimensional analysis, you can determine that the units of KY are moles per meter squared times seconds.
The overall mass transfer coefficient can also be found using literature data. Literature correlations have been developed in order to find both the liquid and gas local mass transfer coefficient. V is equal to the kinematic viscosity that has units of meters squared per second. Gravity has units of meters per second squared. A represents the packing area per bed volume in meters squared per meter cubed. Lowercase d is the nominal packing size, which has units of meters. D represents the diffusivity coefficient of ammonia into water and has units of meters squared per second. Because of all of the way these units cancel out, the value of the mass transfer coefficient is in units of meters per second. As earlier discussed, the experimental mass transfer coefficient had units of moles per meter squared times second. Because we want to be able to compare the theoretical and experimental data, the theoretical mass transfer coefficient will be multiplied by the density and divided by the molar mass. This will give both data sets units of moles per meter squared times second. The same circumstances will apply for the gas local mass transfer coefficient. However, the diffusivity coefficient will now represent the diffusivity of ammonia into air. Also, all of the physical property data will now be for air instead of water. Certain variables in this equation can be reduced to the Schmidt number, the Stanton number, and the Reynolds number. The Schmidt number is a ratio of the diffusivity of momentum to the diffusivity of mass. The Stanton number relates mass transfer velocity to flow velocity. And lastly, the Reynolds number relates inertial forces to viscous forces.
Using the material balance, we can also graphically express absorption on an XY diagram. Here, we have material balances for the vapor and liquid mole fraction. By performing a differential balance from the bottom of the column at y in and x out to any other point on the column, x and y, we can obtain the equation in red. This is also known as the operating line. If you plot the equilibrium line and the operating line on an xy graph, you can obtain the figure shown here where the slope of the operating line is L over V. If you recall that an NTU can be expressed as this integral, you see that the denominator, y minus y star, represents the separation driving force, where y is the mole fraction on the operating line and y star is the mole fraction on the equilibrium line. Looking at this integral, you can see that NTU increases as y minus y star decreases. Smaller NTU values represent easier separation, and you can achieve smaller NTU values by increasing the gap or space between the operating and equilibrium lines. Shown here are figures from our textbook. Looking at the figure on the right, you can see that there is a relationship between the gas flow rate and pressure drop at constant liquid flow rate. Looking at the figure on the left, you can see that the pressure drop also depends on liquid flow rates at constant gas velocity. It is important to consider the pressure in light of flooding as indicated by that dashed line. Mass transfer efficiency significantly drops at flooding, making the pressure drop in a column an important process design consideration. From our textbook, we expected that the pressure drop is proportional to the gas flow rate raised to the 1.86 power. Knowing this correlation, any deviations indicate that the system is approaching flooding.
Here is the apparatus that is utilized in the absorption experiment. The packed column used in this experiment has an inner diameter of 4 inches. The packing was made up of 3/8-inch ratchet rings that were packed to a height of roughly 24 inches. 4 thermocouples were nestled within the packing material so that temperatures could be read. The flow of material throughout the apparatus is represented by this figure, where ammonia is shown in pink, water is shown in blue, and air is shown in red. Water enters at the top of the column and can be controlled using the control valve on the rotometer. Air entered the column using a pressure regulator and the flow meter and controller until it is mixed with another line containing ammonia gas, which is represented on this figure by the green star. Ammonia entered the system through the compressed gas cylinder shown on the left. The ammonia concentration was measured in LabVIEW using the ChillGuard RT infrared ammonia analyzer shown here.
For the absorption lab, proper protective equipment includes a lab coat, gloves, and safety glasses. Due to the use of chemicals in this lab, it is important to know where the safety shower and eye wash station are located. It is important to also note the location of the fire extinguisher and review MSDS sheets before performing the lab. The most significant hazard associated with this lab is the use of ammonia, a toxic and flammable gas. If at any time the ammonia gas is smelled, alert the instructor. Beware of any tripping hazards in the lab and clean up any water spills to avoid slips. Open up the LabVIEW software. This is where all of the instruction guidelines for this lab are located. Switch the airflow valve to on. Double check the airflow meter to ensure that air is flowing. Switch the water flow valve to on. Once the airflow is set to a value of 100 SLM and the water flow rotometer is set to a value of 70, alert the instructor in order to turn on the ammonia source. After Dr. Snyder has turned on the ammonia, you are ready to start running trials. For each trial, adjust the air valve to the desired airflow rate. Also, adjust the water rotometer to the desired flow rate. Use the LabVIEW software and input the water rotometer reading in order to find the flow rate in grams per minute. With a three-way valve pointing towards the bottom of the column, you can start collecting data. Using the charts provided on LabVIEW, wait for the ammonia concentration to stabilize. Once the ammonia concentration has stabilized, point the three-way valve to face towards the top of the column. Wait for the ammonia concentration to stabilize. For the pressure drop trials, the procedure followed will be the same, however, the ammonia supply will be turned off. For shutdown procedure, make sure the professor turns off the ammonia supply. Additionally, make sure that both the air and water supply valves are shut.
This figure shows the results of the ammonia absorption trials and shows the dependence of the number of transfer units on the air flow rate. As you can see, the number of transfer units decreases as the air flow rate increases for a constant liquid flow rate. Thus, a higher air flow rate resulted in a less efficient mass transfer. This figure shows the dependence of NTU now on the water flow rate. As the water flow rate is increased, the number of transfer units also increases. This means that the more water that was running through the column, the more efficient the mass transfer, which makes physical sense because there was more water available to absorb the ammonia. This figure shows the dependence of the height of the transfer unit on the air flow rate. The height of the transfer unit increased as the air flow rate also increased. Because a lower HTU corresponds to a more efficient column, higher air flow rates resulted in less efficient mass transfer. This next figure shows the results of the HTU dependence on the water flow rate. As you can see, as the water flow rate increases, the HTU decreases. Again, this plot demonstrates that higher water flow rates correspond to more efficient mass transfer, as a lower HTU value is observed. The mass transfer coefficients calculated from the experimental data, shown in black, and the theoretical data, shown in red, were compared. As you can see, the theoretical correlations overestimated the mass transfer coefficient. This is likely due to the fact that correlations represent an ideal solution that cannot actually be achieved in real experimental conditions. This final plot shows the pressure drop in the column as a function of both air and liquid flow rates. As you can see, increasing both the air and liquid flow rates causes an increase in pressure drop. The sharp increase in the slope of the line is due to flooding within the column, which significantly decreases the rate of mass transfer.
Aspen Plus software was used to model the absorption column system used in this lab. Aspen Plus does not have a unit op for absorbers, so instead a radfrac distillation column was used. The column was designed to have a 24-inch area packed with ceramic rashid rings with a length and width of 0.375 inches. The column was also designed with a 4-inch inner diameter, operating pressure of 1 atm, and a pressure drop of 0.001 atms. Stream 1 contained pure water, while Stream 2 contained a mixture of air and ammonia. For the outlet streams, Stream 3 contained air with small amounts of ammonia, and Stream 4 contained ammonia and water. A sensitivity analysis was used to determine how the flow rates of water and air affected the concentration of ammonia in Stream 3. Water was varied between 8 and 28 moles per minute, while air was varied between 4 and 9 moles per minute. From the sensitivity analysis, it was found that as the water flow rate increased, the concentration of ammonia in Stream 3 decreased. As the air flow rate was increased, there was a slight decrease in the ammonia vapor concentration. Using the simulation data, the NTUs and HTUs were calculated and used as a comparison to the experimental data. The NTUs calculated in lab and on Aspen were different by a factor of 2 because of the high mass transfer coefficient that Aspen was able to achieve. This figure shows that as the air flow rate increases, HTU will also increase.
During this course, we've acquired some knowledge that we think will help future students be successful. First, divide up the work evenly and in advance. This way every group member knows what part of the report they're responsible for. Second, don't procrastinate writing the report. The best reports are completed days before the deadline so that every group member can edit and review the work. Third, don't be afraid to ask questions. The professors are there to help you. Understanding exactly what their expectations are will help you get a better grade. Last but not least, make sure you get along with your lab group members. You're going to be spending a lot of time together, so communication is really important. Alright, that's it. Lab Group W3B signing off. To all the students watching, these 4 years go by fast. Through all the good times.
Kara, what are you doing? I got into med school!
And the bad times.
I'm so tired, Kara. I literally can't handle my life.
The memories you make along the way are just as important as learning how to be an engineer.